The mystery behind tornado formation. To understand the RFD, we first need to understand what creates a tornado in the first place. Most tornadoes form from supercells, massive rotating thunderstorms that can stretch over 10 miles wide and tower miles into the atmosphere. Inside a supercell, air spins horizontally due to wind shear, strong winds changing direction and speed with height. Updrafts, which are rising currents of warm, moist air, then tilt this horizontal spin into a vertical one, creating a mesocyclone, a rotating column of air inside the storm. That's the core of a supercell and the birthplace of tornadoes. But here's where the RFD comes in. While the mesocyclone spins upward, the RFD crashes downward, and that clash is what gives a tornado its true power. What is the RFD? The rear flank downdraft, or RFD, is a powerful rush of descending air that wraps around the backside of a supercell's rotating core. Imagine a curtain of air crashing toward the ground behind the main updraft. That's the RFD. It forms when cold, dry air from higher in the storm mixes with warm, moist air from near the surface. This mix cools quickly and becomes heavier, sinking rapidly to the ground. When that air hits the surface, it spreads outward, often wrapping around the tornado's circulation, like a whip of wind spiraling around a spinning top. Meteorologists believe this interaction between the mesocyclone's rising air and the RFD's sinking air is what helps a tornado actually touch down. How the RFD helps tornadoes form. Think of the RFD as the final push a storm needs to create a tornado. As the downdraft hits the ground and curls back toward the updraft, it tightens the rotation near the surface, kind of like a figure skater pulling their arms in to spin faster. This tightening increases vorticity, the measure of how fast air is spinning. If conditions are just right, enough instability, wind shear, and moisture, this can stretch that spin vertically, forming a full tornado. Without an RFD, a supercell might rotate all day but never produce a tornado. With a strong, well-placed RFD, you've got a recipe for disaster. The signature look, the clear slot. One of the easiest ways to spot an RFD in action is by looking for what storm chasers call the clear slot, a bright, rain-free area that wraps around the back of the storm. This happens because the RFD clears out rain and debris as it wraps around the mesocyclone. When chasers see that clear slot, especially when it's wrapping tightly, they know a tornado might be moments away. It's often the visual cue that the atmosphere is tightening its grip and something big is about to happen. Warm versus cold RFDs. The critical difference. Not all RFDs are the same. Meteorologists divide them into warm and cold types, and that difference can determine whether a tornado strengthens or dies. A warm RFD is slightly cooler than the surrounding air, but still buoyant enough to feed rising motion. This keeps the tornado's inflow alive, allowing warm air to keep rushing in and powering the circulation. A cold RFD, on the other hand, can choke off the tornado by undercutting it with dense, sinking air. When that happens, the tornado loses its energy source and begins to weaken. In other words, the same process that gives birth to a tornado can also be the one that ends it. What the RFD feels like on the ground for storm chasers and meteorologists in the field, the RFD is both thrilling and dangerous. When it hits, it feels like a sudden blast of wind, often shifting direction and dropping the temperature by several degrees in seconds. Rain can briefly stop as the clear slot moves overhead, a deceptive calm before the chaos. Moments later, the main circulation often tightens, and a tornado can appear from the lowering clouds. Many chasers describe this as a wall of wind, where debris suddenly starts to swirl and visibility drops. If you ever hear that deep, freight train-like roar, there's a good chance you're near the RFD boundary. Real tornadoes shaped by the RFD. Let's look at a few real-world examples. During the El Reno tornado in 2013, one of the largest tornadoes ever recorded, researchers noticed an unusually wide and powerful RFD. It helped create multiple small vortices rotating around the main tornado, making it unpredictable and deadly. In contrast, the Greensburg tornado in 2007 saw a warm, moist RFD that allowed the storm's circulation to strengthen continuously, creating a massive EF5. These examples show that the RFD isn't just an accessory, it's a key player in how tornadoes behave, grow, and even evolve mid-storm. The science behind the downdraft. So what's actually driving all that descending air? It's all about pressure and temperature gradients. Inside a supercell, the updraft creates a region of low pressure, while evaporative cooling within precipitation creates pockets of high pressure nearby. When those cold, dense pockets accelerate downward, gravity takes over. This creates the downdraft, and as it wraps around the updraft, angular momentum increases, feeding the rotation even more. Essentially, the storm is recycling its own energy, using both rising and sinking air to maintain balance, until it can't anymore. RFDS and tornado intensity. Meteorologists often analyze the strength and structure of the RFD to estimate how intense a tornado might become. A strong, moist RFD tends to favor long-lived tornadoes, while a very cold or dry RFD leads to shorter-lived ones. Doppler radar and mobile radar units can now detect wind velocities inside the RFD, allowing scientists to predict whether a storm is entering a tornadic phase. This research has improved warning systems, giving communities precious extra minutes to seek shelter. RFDS and tornado dissipation. Ironically, what gives a tornado life can also cause its death. As a tornado matures, the RFD often grows colder and stronger. Eventually, that outflow cuts off the warm, humid inflow feeding the tornado. Once that connection breaks, the tornado starts to rope out, stretching and weakening before disappearing entirely. This balance between inflow and downdraft is what makes tornadoes so unpredictable and difficult to forecast precisely. Why the RFD is so hard to study. Despite decades of research, the RFD remains one of the least understood parts of tornado formation. That's because it happens low to the ground, hidden by rain, debris, and turbulent winds. Even advanced radar systems struggle to capture its full behavior in real time. That's why field projects like Vortex 2 sent mobile radars and probes directly into supercells to measure temperature, humidity, and wind speed inside the RFD region. Every new mission brings scientists a little closer to decoding its role in tornado life cycles. What the RFD means for tornado safety understanding. The RFD doesn't just help scientists, it helps save lives. If meteorologists can identify when a supercell's RFD is becoming more organized, they can issue tornado warnings earlier. For storm spotters, seeing the clear slot or feeling the sharp temperature drop can signal that a tornado is imminent. That's why storm awareness programs now include RFD recognition as part of severe weather education. Knowing where and how this hidden force moves can mean the difference between sheltering in time or getting caught off guard. The bigger picture, nature's balancing act. The RFD is a perfect example of nature's balance. Rising air meets sinking air, heat meets cold, chaos meets order. It's a reminder that even in destruction, there's complexity and structure. Every tornado that touches down is a brief expression of that balance, born from the atmosphere's constant attempt to even itself out. Understanding the RFD gives us not just insight into tornadoes, but into how fragile and dynamic our planet's weather really is.